Hello everyone. This is a Brucey bonus edition of Periodicity, so part 5. Normally would cover this particular topic as part of atomic structure when we're looking at evidence for electronic orbitals and things like that. So what we are going to look at today is the successive ionisation energies. Along the lines of what we're doing in periodicity in terms of the properties of period 3. And yeah, so we'll make a start on this one. So first off, quick overview of what we're going to be doing. So we're going to look at successive ionisation energies and make predictions based on the information that's provided in terms of what elements it is. Right, recap. So what's an ionisation energy? So we'll just go back to this. And ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, as highlighted by this equation here for sodium. And we're going to look at successive ionisation energies. So in this case, we're then going to be looking at, okay, well this is the first IE, so I'm going to call this I1. So then we might look at I2, which would be taking sodium ions, battering it with a bit of energy, and making an Na2 plus ion. So this would be I2. Okay. I3 would be going from Na2 plus to Na3 plus, and so on. So when we're looking at these, don't get stressed out by the fact that we're making a 2 plus ion from sodium. Sodium, yeah, we know it forms a 1 plus ion when it does any kind of reaction. This isn't a reaction. We are hitting this with energy. We're knocking these electrons off. Okay, we're really battering it. And we will see in a bit on some data where we're knocking off all the electrons of an atom. Close that down. Next slide. Okay, so quick kind of recap of this kind of thing. I've got it summarised on the next page, but I'll go through it now. So what did we find out previously? Well, we saw that the general trend from sodium down here up to argon, the general trend was for an increase across the period. And we also noticed that there was a couple of deviations here and there where they didn't quite fit the trend that we were expecting. And we looked at the explanations for those. And just to go over those ones. So the deviation between magnesium and aluminium. Yeah, so there the aluminium was slightly lower than we expected than magnesium, and this was because the electron that we were removing for that first ionisation energy was coming from the 3p orbital rather than the 3s orbital in magnesium, and this 3p orbital was slightly further from the nucleus, and it's going to be slightly shielded by the s electrons, therefore more easily removed. The second deviation between phosphor and sulfur, this time was when we were going from a case where we had 1 electron in each of the 3p suborbitals, and for sulfur we had a doubly occupied orbital there, and because it's doubly occupied you've got 2 negative electrons in the same suborbital, so you're going to get some repulsion between them, so they're already a higher energy. Right, next slide. Okay, so this is some data on successive ionisations. So this is what we're going to take. So I've just got this little example here. So this is sodium. Okay, so you can see here it's got 11 electrons, so I could say it's 2.A.1. Okay, so that's the sodium atom here. And what we can say is we're going to remove 1 electron. And removing that 1 electron, that's the first IE, that's going to take 496 kilojoules for every mole of these. Okay, in the gaseous state, remember? Then the second ionisation is going from this one, so it's 2.8, and that's Na plus, going to Na2 plus. And this time it's going to take 4,562. then the third, 6, 9, 1, 0. Okay, so we see in sort of rational terms there's quite a big jump here, bigger than here to here. Okay, and I'm going to come back to that in a minute. Okay, so this is for the first view of sodium, so I've also got the last view on this page here. So down here I've got the 9th ionisation energy, so you can see from up here, so I'm going to call this 29K. Okay, next one 141K, next one 159K. So we see here a big jump as we go from the 9th ionisation energy to the 10th ionisation energy. So what we've got to look at is each time we're removing the outermost electron. So I'm just going to look at these ones for an example. So I'm using this electron here. That's the one that's going to be lost from this first case. Okay, so this is coming off from the second energy level. Now this one is coming off from the first energy level. Okay, so we've got to link into these energy levels that it's coming from. Why is it so much harder to remove it from this first energy level than from the second energy level? Or, as the case it was on the previous slide here, why was it easier to remove this electron than it was to remove this electron? It goes back to which energy level we're removing. So this, the 3s1 electron, and the electron that we'll be removing from this one would be a 2p electron. Okay, in this case it was 2p6. Okay, so it was a full set of p's on that case. So why is that? It all comes down to energy levels, distance from nucleus, shielding of other electrons, and all those kind of things. Okay, the further an electron is from the nucleus, the easier it is to remove. As you go closer, it's going to get harder, and you're going to have to put more energy in to remove it. So if we look at these differences between these ones, okay, say 5,000, 7,000, 10,000, 13,000, 16,000, 20,000, 25,000, 29,000, 141,000. So we're getting a big jump here. Here's a big jump, okay? So we're seeing a couple of big jumps, and these big jumps come from when we've changed energy levels. We'll look at another case. Okay, so here I've got 15 electrons to remove, and we can see the data is shown there. Okay, now one way it makes it easier to see what's going on these is to plot what we call the log of the ionisation energy. And for any of you who haven't done logs in maths, what this number is, it's the number that 10 is raised to the power of. So 10 to the power 3.01 equals 1012. So I'm looking at this here. Okay, 10 to the power 3.8 is going to equal 6,274, I beg your pardon. Okay, let's look, well, there's no other nice round numbers in all this. So over here again, 10 to the 4.73, that's going to equal 54,092. Okay, or thereabouts. So what this means is that we can see big changes, almost like order of magnitude changes in these. And if we plot the log of the ionisation energies on the y-axis here against the ionisation number, i.e. which one we're taking off, we can see jumps. So we see a reasonable trend there, and well, they're looking like they're similar. But then we have some jumps. Okay, and these jumps become really important because when we look at where these jumps occur, and I've just highlighted one of them here, it's occurring between the 5th and the 6th ionisation energy here. Okay, so this gives us quite a big clue as to what this element is going to be. Now, it kind of told us this is phosphorus up here, but if we didn't know that, we could have worked this out, because we know once we've got to the 5th ionisation energy, the 6th is coming off from an inner electron shell. And if I look at these on this table of data here, so highlighted are the ones that we've looked at, where we've seen the first big jump for each of them. I'll change it to yellow. Okay, so we're looking where we're going to get a big jump. So here, let's look at this magnesium line here. Oops. And we can see 7,000, 14,000, 1,400, sorry, 7,700. So this is quite a big jump here between these two. Okay, between the 2nd and the 3rd, magnesium's in group 2. Let's look down here. Let's pick, say, chlorine. Okay, so looking at this row here, so chlorine, 1,200, 2,200, 3,800, 5,000, 6,000, 9,000, 11,000, 33,000. Okay, so we've got quite a big jump going on here. 38,000, 44,000, 51,000. Okay, so for chlorine, we can see the big jump occurring between the 7th and the 8th. So then we say, well, what group's chlorine in? Well, it's group 7. So this gives us the clue as to where in the periodic table this atom appears, this element appears, based on the successive ionisation data. So it's telling us where we're going to be removing that electron from. Right, so here we've got just an exam question that's typical of part of a wider exam question. So let's have a look. So an element X is in period 3 of the periodic table. Okay, so we need to know which period it is. It may be period 3. They might make you apply it to something else, period 2 or something like that. And we've got various successive ionisation energies. So we could put in our calculators, work out what the log of these things are. Another way that you could do it is just by looking at the difference between the successive ionisation is. So if I work out what 1577 minus 787 is, so that's 790. The gap between 2nd and 3rd here, so this is 60, 55. Between 3rd and 4th, so 11, 24. Okay, so what we're working out here is how much harder it is each time to remove the next electron. And then between 4th and 5th here, 11,735. So we can see that is where our big jump is occurring. Okay, so we're going from, say, around about 1,000 kilojoules per mole, more difficult for each electron removing each time there, to being 11, nearly 12,000 kilojoules per mole, more difficult to remove the 5th than the 4th. Okay, so from this we can determine that our big jump is occurring between the 4th and the 5th. Therefore, that is when you're moving from energy level to energy level. So removing an electron from the 3rd energy level to the 2nd. So therefore, we must be in group 4. A quick check on your periodic table. Period 3, group 4, that should tell you it's silicon. So you could always go back and just do a mental double check if you wanted and draw out the little Bohr models for these, you know, fill these out and what have you. But the simple thing is just look at what happens there. So the gap where you get the biggest jump, look on the lower side of those, and that's what group it's in. So it's in the 4th group of the periodic table. And just to briefly summarise what we've done today, is we've described how the successive ionisation energy will vary across the period. So the 3rd ionisation energy is not going to be a similar thing for each of them necessarily. And we also explained how the position of the group that an element might sit in can be determined using these successive ionisation energy data. As always, any questions, you let me know. And yeah, see you again soon. Goodbye.